Now let's quickly revisit the performance of a classifier. Your intuition may say that the performance is linked to the number of points that the classifier classified correctly. And yes, this makes sense, and this is definitely a KPI we will look at. But remember the example of credit card transactions. Yeah, if you look at credit card transactions and you try to decide if they're fraudulent or not, you have an imbalanced data set. Yeah? The non-fraudulent transactions you will have 99.3% of the times. Yeah? Whereas the fraudulent ones are only 0.7%. If you're gonna let a machine develop a classifier for this example, the classifier will be very simple. The classifier will say not fraud, not fraud for all X. Yeah? And when the classifier is doing it, the accuracy here, accuracy equals 99.3%. And obviously it's not what we want. We want to get an idea about these ones. So we want to classify these ones correctly. Yeah? So that's why we need more KPIs for classification. All right, let's take a look at an example allowing us to define those KPIs. First, we're going to take a look at a confusion matrix, and it's very confusing, so bear with me. ROC, AUC curve. ROC is receiver operator characteristics. AUC is area under the curve. And we'll take a look at the F1 score. So, what's the example? Well, we will use a binary classifier. Once we have a binary classifier, we know that we have a 2x2 confusion matrix. And we'll look at a feature weight of a person, and then we'll try to predict if that person is obese or not obese. Obese will be in red, not obese in green. So we have a situation where there's one feature here, and the label Y can take two values. Y is 0, not obese, and Y is 1, obese. Yeah? When we will predict obese is if the chance of having the person to be obese is greater or equal than 0.5. Then we will predict Y is 1. In the other case, we will predict Y is 0. So I've drawn a graph of this, so let's go to the other side of the whiteboard. And basically this is the graph. Yeah? We had 10 samples, meaning the weights of 10 people, and 4 of them were not obese and 6 of them were obese. So this is your training data. This is your training data. Yeah? Training. And because we're given the samples, we're given the labels, Y, this is supervised learning. Supervised learning. Okay? Now, we put these on a graph, yeah, where we actually see the weight reflected to a value between 0 and 1, which is what we want. We want a probability score. And this is our 0.5. 0.5 allows us to make these decisions. If it's above 0.5 or equal, it's obese. We predict obese. If it's below, we predict not obese. So that's what you see here. You see this curve here. Yeah? This is typically a curve or the type of curve we will use to convert a linear score weight into a probability between 0 and 1. Yeah, we will discuss these type of curves later on. But if you see, this is my threshold T. Yeah, it is clear that if I'm on this side, I predict obese. If I'm on this side, I predict not obese. Yeah, So that is important when we try to fill out the confusion matrix. What is a confusion matrix? Well, on the top you have the value or the label you predict, whereas on the left you have the actual label. These are the actuals here. These are actuals. And these are our predictions. Okay? So there are a few definitions here. TP means true positive. What does true positive mean? True positive means I predict obese and the person is obese. For your information, NO means not obese and O means obese. And we do this in alphabetical order in the confusion matrix. Yeah? So I predict obese and the person is obese. The ones that I predict obese, that transform this weight into something in this bracket, 1, 2, 3, 4, 5, 6, 6 people here that I predict obese, but only 5 are truly obese. This green fellow is not obese. So we have 5 true positives. Now let's take a look at the true negatives. A true negative means I predict not obese and the person is not obese. So here I predict not obese and the person is not obese. 1, 2, 3. The 3 green ones are true negatives. What's a false positive? Well, I predict obese and the person is not obese. That's this green fellow here. Yeah? So that's 1. And a false negative means I predict not obese, but the person is obese. That's the red fellow here. Okay? Now, in statistics, false positive we also call type 1 error. Whereas false negative we call type 2 error. Okay? There is a trade-off between type 1 and type 2 error. And what does it actually mean? We'll take a look at that, but first let us go to some KPIs. Accuracy is, the logical KPI is out of all samples, how many did you classify correctly? So all samples here, we had 10 people, and we have 8 correct. The true negatives and the true positives were correct, so it's 8 out of 10, so it's 80%. Yeah? Now we take a look at a KPI called recall. Recall is the true positives divided by true positives plus false negatives. So in our case, it is true positives is 5. Yeah? And true positives plus false negatives is 6. So that's about 83%. Precision is true positives divided by true positives plus false positives. So it's again 5 on top, and that is 6, also 83%. Now there is a trade-off between type 1 and type 2 error. Yeah? Meaning if you want to reduce type 1 error, you're going to automatically increase type 2 error. Now which one do you actually want? The difference is this one here. Is false negative and false positive. The other parameters here are the same. So you gotta decide what you can live with. Can you live with false positives or can you live with false negatives? I give you an example. Assume that we build a classifier that predicts if people have cancer or no cancer. Yeah? So what's a false positive? Let's go there. That's precision. False positive means I predict that the person has cancer, yeah, but the person does not have cancer actually. Is that bad? Yeah, it's bad because you're gonna make a person worried for a while. But let us look at the alternative. The alternative is false negatives. That means I predict that the person has no cancer, but the person actually has cancer. Yeah? This is far more worse than the type 1 error. Yeah? Because here you can have a person worried for a while, but here the person may not get treatment and may die. So you could decide that I don't want any false negatives. If you don't want false negatives, this is 0, your recall is going to be 1. Yeah? So this is how you have to deal with this. Yeah? What we're going to do now is, you've seen that in order to come to this rule, we put the threshold t just in the middle. Well, we don't need to. We can put this threshold wherever we want to. So, and that is what we will deal with in ROC and AUC.